Welcome to lecture 27 of Introduction to Quantum Field Theory. In this lecture, I will continue the discussion of the O and vector model that we started in the last lecture. In the last lecture, we solved the O and vector model and the large N limit. We found a result that says that the pressure of the O and vector model is given as n times the pressure of a free real scalar field with a funny mass term minus a correction term, both of which depend on this parameter zeta tilde that itself is the location of a saddle point condition given or reproduced here. In this lecture, we want to discuss the renormalization of this O and vector model pressure because the free scalar field pressure itself is still divergent. And to simplify the discussion, I will talk about the case where we set the mass parameter here to 0. This is a simplification in terms of the technicalities involved. However, it is not necessary for non-perturbative renormalization of the model. In the MS bar scheme in dimensional regularization, we found the following result for the pressure of a single real scalar field in 3+1 dimensions. It's reproduced in equation 27.3. And in dimensional regularization, this result here is divergent because it is proportional to 1 over epsilon here, where epsilon still needs to be sent to 0. We want to set the mass parameter to 0. That's what I said in the previous slide. However, the saddle point condition that I'll just show here again involves the free scalar field pressure evaluated at a funny mass term. So even if we set m to 0 here, the effective mass that we want to evaluate the pressure at is still given by a non-vanishing parameter. Hence, we want to sort of keep this result here general. To simplify notation, I'll write I times zeta tilde just as x, and setting m to 0, the saddle point condition given in the previous slide, then becomes the following equation here, where x is supposed to be a solution of this equation. The physical result for the pressure of the ON model depends on the value of the saddle x. If the saddle x is a non-perturbative solution from the equation that I just showed on the previous slide, and as such, it's not really possible to get anywhere if we try to expand in perturbation theory because we want to have a non-perturbative result. However, we find that in this case, it's actually simple to perform a non-perturbative renormalization, simply by noticing that if we take together these two terms here, the divergent term that comes in with a 1 over epsilon and the coupling constant in the Lagrangian, and we sort of add this together to find a renormalized coupling constant lambda physical, then the resulting saddle point condition will be finite. The result here is non-perturbative because in perturbative renormalization, we always rewrote the parameter in the Lagrangian lambda as some bare parameter and a counter term. Clearly, since this involves inverse quantities, this is a non-perturbative renormalization constant. It involves an infinite number of terms in terms of the powers of the original coupling constant. Nevertheless, if we use this non-perturbative renormalization condition and we plug it into the saddle point condition, we find that all the appearances of the divergent parameter epsilon vanish. We can send epsilon to 0, and we find that this saddle point condition here is finite and presumably also has finite solutions for the saddle point x. If we use the same notation, rewriting sigma tilde in terms of x and setting m to 0, the pressure of the ON vector model is then given by the expression here. And what you should notice is that it also has this divergent 1 over epsilon that originally sort of appeared. However, if we use the same renormalization condition as before, namely we sort of lump together the 1 over epsilon with respect to the bare coupling constant lambda, we find that these two sort of conspire in such a way that the same non-perturbative renormalization gives us a finite result for the pressure in the MS bar. So what we find is that in the large N limit, the ON model is non-perturbatively renormalizable, and that for the zero mass case in dimensional regularization, the theory really only requires coupling constant renormalization. In particular, we don't need any cosmological counterterms that we had to introduce in the usual discussion that followed the free scalar field cosmological constant. So basically, if we renormalize the coupling constant, the ON vector model pressure is automatically finite in dimensional regularization. So it can be evaluated non-perturbatively, and we can study the properties of this solution. Recall first that because the pressure is a physical quantity, as such, it cannot depend on the arbitrary choice of the renormalization scale mu bar. And just like we discussed in the lecture on the renormalization group, lecture 21, we find that the independence of the pressure with respect to dependence of mu bar, meaning the derivative of this quantity has to vanish, gives us a condition on the dependence on the physical parameter. So basically, we solve this apparent paradox by saying that any dependence that's explicitly on mu bar and the pressure has to be cancelled by the dependence of the coupling constant on that renormalization scale. So we find that if we impose that a physical quantity cannot depend on mu bar, we find that this gives the following condition on the coupling constant lambda physical. I just want to note that in order to get this simple expression, it is best to use the stationarity condition because we know we have, in addition to the usual pressure, the condition on the saddle point, which is precisely this derivative here, in order to simplify what we write down there. So if this condition has to hold, we find that the coupling constant has to have a particular form, and introducing again the notation for the beta function of the theory, we find that beta here is given as lambda squared over pi squared. And since we have not made any approximations here, everything was exact in the large N limit. This is the exact beta function for the ON vector model for all values of lambda. Because the beta function is positive for all values of lambda, there's no perturbation theory involved. We can just integrate the beta function and find the explicit running of the coupling for the ON vector model. It's just given as 2 pi squared logarithm of mu 0 squared over mu bar squared. The mu 0 squared here is essentially, in principle, an integration parameter. However, we were discussing this particular parameter here. In particular, this mu 0 here is also known as the lambda pole of the theory, because whenever mu bar, our renormalization scale, is equal to this integration constant mu 0, the logarithm has an argument of 1, so logarithm of 1 is 0, and we get that the coupling constant at this scale, at the lambda pole, is actually divergent. So this happens, meaning the divergence of the coupling constant happens as a finite scale mu naught. Just inspecting again this form here, we find that for small values of the renormalization scale mu bar, the argument of the logarithm is big, and since the logarithm is in the denominator, the expression is small. So our small coupling corresponds to small energy scales, but it grows as the scale mu bar grows, just as the discussion we had in lecture 21. Because at a finite scale mu bar equal to mu 0, the coupling constant diverges, that means that we cannot access very high scales. We cannot access mu bar going to infinity. And since high energy scales correspond to very small distances, this means that the ON vector model does not have a good continuum limit. We must treat it as an effective theory that's only valid down to a certain finite distance or up to a certain energy scale. And this finite energy scale certainly is given by the lambda pole mu 0. In practice, what we need to do is we need to stop trusting the result of the theory whenever we are asking questions at an energy scale mu bar that becomes close to the lambda pole. So we need to stay at energy scales much, much smaller than the location of the lambda pole mu zero. So let us now discuss a little bit what the model has to say about the cosmological constant. Recall that the cosmological constant is essentially given by the pressure at zero temperature. Unlike other theories we discussed, such as the free scalar field, the cosmological constant in the ON model is finite, and it can be calculated in the following way. So in dimensional regularization, this result is finite. So we found that this is the result we got. And we can plug in the explicit form of the coupling constant, lambda physical of mu bar. And then this expression here simplifies, and we get that the zero temperature pressure, the cosmological constant, is just given by this expression here, where x here again is just the solution to the saddle point condition, which again at zero temperatures just simplifies to the following form here. Now let us first discuss the solution to the saddle point condition. If we use this saddle point condition here, we can recognize that the pressure can be written in terms of the saddle point condition, where the only difference here is the exponential e to the 3/2 in case of the pressure and e to the 1/2 in case of the saddle point condition. So we find that the pressure here can be simply written as nx over 16 pi squared, where x is the solution to the saddle point condition. The saddle point condition itself has two solutions. So back up. Saddle point condition has two solutions. One of them is x is 0, and the other one is x being such that the argument of the logarithm vanishes. X is 0 is one of them, and the other one, x, is mu squared, mu naught squared, e to the 1/2 over 2. The solution x that is non-vanishing is proportional to the lambda pole. So basically, this is a very high energy scale. It is proportional to the lambda pole itself. So at this scale, we really don't trust that the field theory can be sort of thought of as an exact theory because it's breaking down. We must discard this solution here. So the only solution that's a valid solution is the solution x is 0. For x is 0, the pressure or the cosmological constant just vanishes, and that's the result we get. So we find that within dimensional regularization, we get a result for the cosmological constant that says that the cosmological constant is exactly vanishing, which itself seems to be a very appealing result because basically we sort of usually sort of associate this with sort of measurements of the cosmological constant in space. However, you have to recall that we got this result in dimensional regularization, which only cares about logarithmic divergences. If we were to repeat this analysis, for instance, in cutoff regularization, we would find that the zero temperature pressure would indeed still contain terms like cutoff to the 4, cutoff squared, and so on, just as we discussed in lecture 11. These terms would then suggest that we would need additional counter terms in order to cancel these divergences in cutoff regularization. So the point is that in terms of calculating the cosmological constant, the results obtained in dimensional regularization have certainly to be interpreted with great care because we don't see these counter terms that come in this way. For other properties that may not be sort of a strong constraint, but for the cosmological constant, it certainly makes results tricky to interpret, and it's easy to sort of come to wrong conclusions. And this concludes the present lecture.